We are going to be learning about two-dimensional momentum conservation. Last year, you learned about conservation of momentum in one dimension. You also learned about vectors in multiple dimensions. So we're just going to put those two things together, and then we will apply it to what we're learning in particle physics. I have an example problem for you that we're going to do. You'll do a lab, and then we'll apply it to what we're doing now. So let's say that we have a red ball, which has a mass of 3 kilograms, moving at 5 meters per second to the right. It collides with the black ball, which has a mass of 4 kilograms and is initially at rest. After the collision, the black ball, so this is a glancing collision, it's not a head-on collision, the black ball moves at 3 meters per second at 40 degrees north of east, and we want to know the final velocity of the red ball. And we're going to use momentum conservation to solve this. Momentum is a vector, and it is conserved in the x direction independently of being conserved in the y direction. So basically all we're going to do is split this motion up into x direction and y direction, apply conservation of momentum in the x direction, apply it in the y direction, and then we'll bring them back together for the final answer. So we know initial momentum in the x direction is equal to final momentum in the x direction. We also know initial momentum in the y direction is equal to final momentum in the y direction. So the first thing we need to do is split this velocity into x and y components so that we can apply it in our x and y directions. So I have this velocity of 3 meters per second, and it's at a 40-degree angle. So if I want my velocity in the y direction, I get 3 times the sine of 40 degrees, and that will give me 1.93 meters per second. And then my velocity in the x direction will be 3 times the cosine of 40 degrees, which will give me 2.30 meters per second. Now I can write my conservation of momentum equations for the x direction and the y direction. So initially only the red ball is moving. So the initial momentum of the red ball in the x direction is equal to the final momentum of the black ball in the x direction plus the final momentum of the red ball in the x direction. Initial momentum of the red ball in the x direction is going to be mass of the red ball times velocity initial of the red ball in the x direction. Momentum of the black ball will be mass of the black ball times velocity final of the black ball in the x direction, plus mass of, and then momentum of the red ball, so plus mass of the red ball times velocity final of the red ball in the x direction. So I can isolate from my unknown variable. I know my mass of my red. I know the initial velocity in the x direction of the red. I know my mass of black, and I know the final velocity of the black in the x direction. I know the mass of the red. This is the one I don't know, the final velocity of the red ball in the x direction. So I'm going to subtract this over, and then I'm going to divide by mass of red. So I get V final of the red ball in the x direction equals mass of red times V initial red in the x minus mass of black times V final black in the x over mass of red. And I can plug in numbers there. Mass of red is 3 kilograms. Initial velocity of red in the x is 5 meters per second, minus mass of black, which is 4 kilograms, times the velocity of black in the x direction final, which is 2.3 meters per second, divided by the mass of the red ball, which is 3 kilograms. And I get that the final velocity of the red ball in the x direction is 1.93 meters per second. So now I do the same thing in the y direction. I have the initial velocity, or the initial momentum in the y direction is 0, right? Because the red ball is the only thing moving initially, and it's not moving in the y direction. So we just put 0 equals momentum final of the red ball in the y direction I'm going to write this without vectors. So I'm going to subtract momentum final of the black ball in the y direction. Now, we know that if there's no momentum initially in the y direction, and this one has momentum upward in the y direction afterwards, then the red one has to have that same momentum downward because they have to cancel each other out to get no momentum. So we know that those y components of momentum are going to be equal to each other. So I'm going to set those equal to each other, and then I'm going to say momentum is mass times velocity. So mass of the red ball times the velocity final of the red ball in the y direction equals mass of the black ball times velocity final of the black ball in the y direction. And then I'm solving for the final velocity of the red ball in the y direction. So I get v final of the red ball in the y direction equals v fry. Mass of the black ball times velocity final of the black ball in the y direction over mass of the red ball. And I can plug in numbers there. Mass of the black ball is 4 kilograms. Final velocity of the black ball in the y direction is 1.93 meters per second. And then we divide by the mass of the red ball, which is 3 kilograms. So our velocity final in the y direction of the red ball is equal to 2.57 meters per second. Now we're not done. We have the final velocity in the x direction and the y direction. Now we need to use our vector rules to combine them to find the total velocity. So I'm making a little box here. I'm running out of room on my tiny whiteboard. We have the velocity in the x direction, velocity in the y direction. Our x direction is 1.93 meters per second. Our y direction, this is not drawn to scale, is 2.57 meters per second. So we use Pythagorean theorem to figure out what the total velocity is. And that is, so that'll be the square root of 2.57 squared plus 1.93 squared. So the velocity final is 3.21 meters per second. And then I use like the tan inverse to find the angle. Scratch that. This is going to be down, right? Sorry about that. Because that one went up. So this one has to go down. So it's going to be like this instead. Then we need to find this angle theta. So we do the tan inverse of 2.57 over 1.93, and that's going to give us theta equals 53.1 degrees, and that's going to be south of east because this one went north. So this one has to go south. There it is.